In this lesson, we are going to look at the function of gyroscopes and the gyroscopic properties of rigidity and precession. We will also look at gyroscopic wander, real and apparent. The gyroscope, or gyro, provides a stable reference datum, which is unaffected by the manoeuvres of the aircraft. As well as a direction or heading reference, gyros can also provide an attitude reference. On aircraft, gyros provide the basis for the directional gyro indicator, or DGI, the artificial horizon, the turn and slip indicator, or turn coordinator, gyromagnetic compasses, inertial navigation systems and inertial reference systems, yaw dampers, the autopilot, and stabilization of radar scanners. They are also used for many other applications. The simplest form of gyro consists of a spinning disc called a rotor. The shaft which the rotor spins around is called the axis. Gyros are defined in their orientation as either horizontal or vertical by reference to their spin axis, and not the rotor. Gyros have two basic properties. These are rigidity and precession, and we will look at each one in turn. Rigidity is the ability of a spinning rotor to maintain its axis in a fixed direction in space, unless subjected to an external force. It is caused by the inertia of the spinning mass of the rotor, and rigidity is sometimes referred to as gyroscopic inertia. The rigidity of a spinning rotor is affected by three factors. The first of these is the rotor mass. The second is the effective radius at which the mass acts. And the third is the speed of rotation. The rigidity of a gyro can be increased in four ways. The first way is to increase the mass of the rotor. The second way is to increase the diameter of the rotor. The third is to concentrate the greater part of the mass around the perimeter of the rotor. And finally, we can increase the speed of rotation. The second property is precession. Let's follow the definition carefully. It is important to understand the effect of precession when we consider gyros. If an external force is applied to change the direction of the rotor spin axis, the gyro resists the change, and instead moves the force at right angles to the direction originally applied. This is precession. The rule of precession states that the gyro will precess at 90 degrees to the applied force measured around the circumference of the rotor in the direction of spin. In other words, the force applied will appear to have moved 90 degrees around the rim of the rotor in the direction of the gyro rotation. Let's see how this works in practice. In the example here, the gyro rotor is stationary. Let's apply a force to one side of the spin axis in a vertically upwards direction. We would expect the rotor to tip backwards, and indeed it does. Now let's spin the rotor and apply the same upwards force to the spin axis. We might still expect the gyro to fall backwards. But now, because of the effect of precession, the upwards force we have applied is transferred 90 degrees in the direction of rotation, and instead the gyro moves in the direction shown. Note that the rate at which the gyro will precess is directly proportional to the force applied, and inversely proportional to the mass and rotational speed of the rotor. This means that precession and rigidity have opposite characteristics. If a gyro has a lot of rigidity, it will not precess very much. If it precesses a lot, it cannot be very rigid. In order for a gyro to maintain its axis fixed to a point in space, the gyro is mounted in a suspension system known as a gimbal ring or gimbal. Aircraft gyros generally have one or two gimbals. In the example we can see here, the spin axis of the rotor is carried by a gimbal cage, which is pivoted at each end to allow the assembly the freedom to rotate around the axis marked XX. This arrangement is known as a single gimbal system, which allows 1 degree of freedom. If the XX axis is assumed to be the longitudinal or fore and aft axis of the aircraft, we can see that the aircraft can pitch up or down and bank without disturbing the rotor spin axis away from its fixed point in space. We can also see that with a single gimbal system, if the aircraft was to yaw, the rotor spin axis would be forced sideways out of its original orientation. However, there are instances where freedom to yaw is required, in addition to the freedom to pitch and roll. And the solution is to mount the gimbal within a second gimbal, as we can see here. We will call the first gimbal we looked at the inner gimbal, and the second gimbal the outer gimbal. Note that a two-gimbal system is described as having 2 degrees of freedom, or full freedom. By convention, the degrees of freedom of a gyroscope do not include its own spin axis. Any departure of the gyro spin axis away from its fixed orientation is known as gyro wander. Wander may be either real wander or apparent wander, or a combination of both. And in addition, wander may be further subdivided into categories known as drift or topple. We will look at drift and topple first. Whether a gyro is said to drift or topple depends on the direction in which the gyro spin axis moves away from its original orientation. Gyro drift occurs when the spin axis moves in a horizontal plane. Gyro topple occurs when the spin axis moves in a vertical plane. Note that vertical axis gyros can only topple, whereas horizontal axis gyros can be subject to both drift and topple. Let's look now at real and apparent wander. Real wander occurs when the gyro spin axis actually moves away from its originally fixed direction in space. Real wander may result from manufacturing imperfections or wear. A perfect gyro with no external forces on it should not suffer from real wander. Typical causes are imbalance in the mass of the rotor, imperfectly balanced gimbals, and uneven rotor bearing friction. Apparent wander can be drift or topple, and it is said to occur whenever the spin axis of an otherwise perfect gyro appears to an earthbound observer to be changing direction. The cause of this can be either one of 2 factors, or a combination of both. The first factor is known as earth rate. The second factor is known as transport wander. We will look at each in turn, starting with earth rate. Earth rate occurs because of the rotation of the Earth. To understand the effect of earth rate, all we have to do is to remember that one of the properties of a gyro is its ability to maintain its spin axis in a fixed direction in space. The Earth, however, rotates around its own spin axis. So let us suppose we are in an aircraft which is parked on the ground in the northern hemisphere at location A. The aircraft is facing towards the true geographic North Pole, and we will align the spin axis of the gyro in the same direction also. We will call this gyro North, or GN. If we now attach a compass rose to the spin axis of the gyro, we will see that while the Earth is rotating on its own spin axis, the gyro spin axis remains in a fixed direction in space. So we can see that in this particular example, where the aircraft is in the northern hemisphere, the direction of true north in relation to our gyro north appears to decrease. Note that in the northern hemisphere there will always be a decrease, and for this reason the Earth rate is designated negative, or for mathematical purposes it is given a minus sign. In the southern hemisphere the opposite applies, and the Earth rate is designated positive and is given a plus sign. Remember though, neither our aircraft orientation on the surface of the Earth nor the spin axis orientation of the gyro have altered. It is the Earth rotation around its own axis which has caused the change. In effect, apparent drift due to the Earth rate arises from the convergence of the Earth's meridians. So at the equator, we can see that there will be no apparent drift, as the Earth's meridians are parallel at this point. Whereas at the poles, there is maximum convergence. At the poles, the apparent drift will be equal to the rate of Earth rotation, which is 15 degrees per hour. The apparent drift experienced, therefore, due to Earth rotation, will depend on the latitude under consideration. So a mathematical formula can be devised, which will give us the amount of apparent drift experienced at any latitude due to Earth rate. In the formula, the rate of change due to Earth rotation, or just simply the Earth rate, equals 15 times the sine of the latitude in degrees per hour. Let's now look at apparent topple as opposed to apparent drift. If we think about it, it can be seen that apparent topple will be at its maximum of 15 degrees per hour at the equator, and will be 0 at the geographic poles. The formula for apparent topple due to Earth rate is topple equals 15 times the cosine of the latitude in degrees per hour. The second factor which causes apparent wander to an earthbound observer is known as transport wander. This occurs when the gyro is transported in either an easterly or westerly direction across the Earth, at latitudes other than the equator. As with apparent wander due to Earth rate, the gyro spin axis remains fixed to a point in space. But with transport wander, apparent drift or topple occurs because the location of the gyro moves. Transport wander occurs at the same time as Earth rate, and in the northern hemisphere, the effect of the Earth rotation will increase the rate of apparent drift in an easterly direction, because the aircraft and Earth are both moving in the same direction. While Earth rotation will reduce the rate of apparent drift due to transport wander in a westerly direction, because the Earth and the aircraft are moving in opposing directions. Transport wander in an easterly direction in the northern hemisphere is designated negative, and mathematically it is given a minus sign. Transport wander in a westerly direction in the northern hemisphere is designated positive, and is given a plus sign. In the southern hemisphere, the opposite rules will apply. Note also that transport wander will not affect flights along a north or south meridian. The formula to note for transport wander is transport wander equals the easterly component of ground speed divided by 60 times the tan of the latitude in degrees per hour. To conclude, let's do a sample calculation to see the actual effects of earth rate and transport wonder on a directional gyro reading. A directional gyro is said to read 270 degrees. The aircraft flies for 80 minutes along a track of 270 degrees true, along the parallel of 20 degrees north, at a ground speed of 540 knots. What is the gyro reading at the end of the flight if there is no change in the aircraft's true track? Let's go through the calculation together. We know earth rate equals 15 times the sine of the latitude in degrees per hour. And the mathematical sign for earth rate in the northern hemisphere is minus. Transport wonder equals the easterly component of ground speed divided by 60 times the tan of the latitude in degrees per hour. And we know the mathematical sign for transport wonder in a westerly direction in the northern hemisphere is plus. Both earth rate and transport wonder are relevant to the final reading on the gyro. So adding earth rate and transport wonder together, we get a total of minus 1.854, or minus 1.854 degrees per hour. After 80 minutes, the change will be minus 2.5 degrees. So the gyro will read 270 degrees minus 2.5 degrees, which is 267.5 degrees. Compare this answer to the answer we would get if the aircraft was travelling east along a track of 090 degrees true, to appreciate the difference travelling either eastwards or westwards will have as a result of earth rotation and transport wonder. The lesson on the directional gyro indicator, or DGI, examines this matter again. This concludes the lesson on gyroscopic theory. A summary of gyro wonder and the main points we have covered in this lesson follows. The gyro provides a stable reference datum, which is unaffected by the manoeuvres of the aircraft. The simplest form of gyro consists of a spinning disc, called the rotor. The shaft which the rotor spins around is called the axis. Gyros are defined in their orientation as horizontal or vertical, by reference to their spin axis. The two basic properties of gyros are rigidity and precession. Factors affecting rigidity are the rotor mass, the effective radius at which the mass acts, and the speed of rotation. Rigidity can be increased by increasing the mass of the rotor, increasing its diameter, concentrating greater mass around the motor perimeter, and by increasing the speed of rotor rotation. The rule of precession states that a gyro will precess at 90 degrees to the applied force measured around the circumference of the rotor in the direction of spin. Precession is directly proportional to the force applied and inversely proportional to the mass and rotational speed of the rotor. If a gyro has a lot of rigidity, it will not precess very much. If it precesses a lot, it cannot be very rigid. Aircraft gyros generally have one or two gimbals. By convention, the degrees of freedom of a gyroscope do not include its own spin axis. A two-gimbal system has 2 degrees of freedom, or full freedom. Any departure of the gyro spin axis away from its fixed orientation is known as gyro wonder. Gyro wonder may be real or apparent, or a combination of both. Both real or apparent wonder may be subdivided into drift or topple. Gyro drift occurs when the spin axis moves in the horizontal plane. Gyro topple occurs when the spin axis moves in the vertical plane. Vertical axis gyros can only topple. Horizontal axis gyros can drift and topple. Real wander is actual movement of the spin axis. Apparent wander can be drift or topple due to earth rate or transport wander. The formula for apparent drift due to earth rate is earth rate equals 15 times the sine of the latitude in degrees per hour. Transport wander occurs when the gyro is transported in an easterly or westerly direction across the Earth, at latitudes other than the equator. The formula for apparent topple due to earth rate is apparent topple equals 15 times the cosine of the latitude in degrees per hour. The formula for transport wander is transport wander equals the easterly component of ground speed divided by 60 times the tan of the latitude in degrees per hour.